Our world is populated with numerals, but we rarely stop to think about them. Where did they originate? How did they evolve? Well, the answer is the numbers we use today evolved in India. And the story of how they moved across the world is a fascinating one. Welcome to this episode of the Maths Factor, where we are going to explore the intricacies of our number system. We will become world travelers to see how numbers have evolved in different systems. We're also going to show you how both animals and babies can understand numbers intuitively. So gear up as we kickstart our journey right away. As civilization started to develop across the world, there surfaced the need for notation and for numerals, the need for keeping records. But before we start tracking these developments, let's see if you know the difference between numbers and numerals. Well, it's quite simple. The number is the idea. The numeral is the notation. The first stop on our journey is South America in the 1400s, the land of the Incas. This is Machu Picchu, the famous Inca site that lay forgotten for centuries. This urban creation is a testament to how advanced the Incas were as a civilization. They had roads, textiles, cities, agriculture, and government. Now, curiously, they seem to have had no written language. Now, when the Spanish conquistadors landed in South America in 1532 CE, they found no sign of written numeral records. What they did find, huge amount of knotted ropes, like this. These were no normal ropes. In fact, they were called quippers. They were a way of recording information that were unique to this region. Shall we try our hand at making a quippu? Mrinal here is an eccentric lawyer who's going to try and categorize the books in a library using a quippu. She needs to separate her journals, case books and fiction. She first takes strings of many different colors and then starts by tying knots in them. She has 121 journals, so on the first rope, which is yellow, she makes 1, then 2, then 1 knot, like this, which means 121. She uses a red string to show she has 31 case books and an orange string to note she has 12 fiction books. And the last strand, which is green, is used to tally them all up, 264. Mrinal has made a quippu that effectively categorizes her library. Real quippus were much more complex than this. Some had hundreds of strings and extra strings tied to ones hanging from the base. It is important to remember that the quippu is not a calculating device. It is just a way to store numbers. There were even special people who were in charge of deciphering the quippu, called Kippukamayaks, or keeper of the quippu. Okay, from South America we move to ancient Egypt and Babylon. First to Egypt all the way back in 3000 BC. When we look at the pyramids and the temples constructed at that time, it is clear that a degree of mathematical sophistication was needed to build these. Some of our most important understanding of the mathematics of ancient Egypt comes from two papyruses known as the Rind Papyrus and Moscow Papyrus. These were not treatises, but broadly lists of practical problems which were used to train people in mathematics. The Rhind papyrus contains 87 problems, while the Moscow papyrus contains 25. The Egyptian numeral system is visible both in artworks from the time and in monuments. From these, it is clear that they use maths in agriculture, surveying, and trading. Let's take a quick look at how their numbers worked. The Egyptians used hieroglyphics or pictorial signs to denote numbers. They had a special system for every power of 10, which looked a bit like this. This was 1, 10, 100, 1,000, 10,000, 100,000, 1 million. So they could write numbers all the way to 1 million. They used to use repetition to write a number. So 4,622 would look like this. Now the problem arose because they did not have a place system. Wondering why that was a problem? Well, writing 1 million was simple, but writing 99,999 required 45 symbols. This moved from Egypt to ancient Babylon, where numerals were developed about 5,000 years ago. Unlike the Egyptians, who counted in groups of 10, the Babylonians counted in groups of 60. So how did their numerals work? Any number less than 10 had a wedge that pointed down, so 4 would look like this. The number 10 was symbolized by a wedge pointing to the left, so 20 would be. Numbers less than 60 were made by combining the symbols of 1 and 10, so 47 would look like this. And from 60, they would start all over again. So this is what 64 would be like. So they didn't have a symbol for 0, but they did use the idea of 0. When they wanted to express 0, they just left a blank space in the number they were writing. So if it is 60, there would be a single wedge mark and a dash. When they wrote 120, they would put 2 wedge marks and a little dash in the second place. The Babylonian calendar worked in the unit of 60. Year had 360 days. Each day was divided into 24 hours, each hour into 60 minutes, and each minute to 60 seconds. And this form of counting has survived for 4,000 years. We've been traveling across the ancient world to see different forms of numerals. We could keep going. The Mayans, the Greeks, and the ancient Romans developed their own unique counting systems. We've dropped the Mayan and the Greek ways, but we still use Roman numbers today, for clocks, to denote centuries, to suffix the names of kings and tombstones, etc. Let's now see how numbers come naturally to most of us, even animals. Take a bird. She has a nest with 4 eggs. If you take 1 out, she may not notice, but when you take 2 out, she will desert the nest because she has realized that there is a predator somewhere close. This means she can tell between 2 and 3. Sounds random? Well, let me share a more documented experiment done on bees by a group of scientists from the Vision Centre in Australia. The scientists showed the bees a number. So if it was 3, there would be 3 dots. Then they flew through a tunnel into another chamber. Here they were faced with 2 forks, one with 3 and the other with some other number, say 4 dots. Now, If the bee picked the same number, in this case 3, the scientists added an incentive. They got a hidden sugar solution as a reward at the end of the fork. If they chose the wrong pattern, they were released and allowed to try again. And the bees did pretty well. They were more often than not chose the same pattern that they had seen earlier. To show that they were recognizing numbers and not just shapes, the scientists would vary the representation of the number. So they would first show the bees 3 dots, and then the next fork would have 3 stars. By the end of the experiment, the scientists were able to conclude that the bees could count till 2, 3, and sometimes till 4. Similar experiments have been done with chicks, pigeons, and monkeys, to name a few. And from this, we are able to conclude that animals are able to discriminate between small numbers. What about babies? And I mean tiny ones who haven't started walking or talking and clearly haven't been taught numbers. Let's look at an experiment done by Karen Wynn, a scientist in the US, with a group of 32 5-month-old infants in 1992. Let us see how young Vani reacts to the same stimuli. She is first shown a doll that is then hidden behind a screen. Then another doll is added to the one behind the screen. Now if Vani sees a number she expects, she does not react. So if there are 2 dolls behind the screen, which is the possible event, there is little reaction. However, if there is a number that she does not expect, she clearly notices. So if there is 1 doll behind the screen and she hadn't seen the second being removed, she would be surprised. How do we know that she has noticed? Well, because she looks at the objects for much longer. Similarly, if there are 2 dolls to start off with and one is removed, Vani is able to perceive the difference between the right answer and the wrong, which implies that infants are capable of distinguishing between small numbers. This result caused much consternation when first published and had many disbelievers, but independent research from other sources have confirmed Wynn's findings. Great. So it looks like humans and animals both have an innate number sense. But as mankind progressed, what they developed was a numeral system to make sense of these numbers. We are back to exploring the evolution of the numeral system. We've already seen how Egyptians, Babylonians, Incas, and Romans handled numbers. But none of those systems are very much in vogue today. The system we use today, the system the whole world is familiar with, is known as the Indo-Arabic system. To explore the system, we'll need to travel to ancient India and explore the mathematics of this region. So what kinds of numerals were used in India? Some early evidence is found on columns erected in India by King Ashoka in about 250 BC. Similar inscriptions are found in caves near Pune 100 BC and Nasik 200 BC. These numerals appear in a script called Brahmi. The Brahmi script, which had notations for numbers 1 to 9 as well as distinct symbols for a host of other numbers. However, what they didn't use was a 0. One important source of information on this topic is the writer Al-Biruni. Al-Biruni, who was born in modern-day Uzbekistan, came to India first in 1030. Through his numerous visits, he studied and documented the Indian number system. He realized that number systems often varied across different regions. For example, the Tamils in the south of India had also evolved another numeral system, the Tamil Brahmi numbers. Various stone inscriptions and pots show evidence of this, and most of this inscription dates back to the 1st and 2nd century AD. Now, all these numbers eventually evolved into what came to be known as the Indo-Arabic numeric system. Let's explore how this system works. It has 4 defining characteristics. First, it uses 10 digits, 0, 1, 2 till 9. It groups these by 10, so 10 ones are replaced by 10. Similarly, 10 tens are replaced by 100, 10 hundreds are replaced by 1000, and so forth. Thirdly, it uses a place value, starting from right to left. So the first number represents how many ones there are, the second number represents how many tens there are, the third how many hundreds, and so on. So if we have 22 crayons, we will group 2 groups of 10 and we'll have 2 left over. We will write 22 like this. If we have 124 crayons, we have 1 group of 100, 2 groups of 10s, and 4 singles. We will write 124 like this. Finally, the system is additive and multiplicative. So if we take 124, the value of the numeral is found by multiplying each place value by its corresponding digit and then adding the resulting products. So the numeral value is equal to 1 into 100 plus 2 into 10 plus 4 into 1. 100 plus 20 plus 4, 124. It all sounds pretty simple and obvious, doesn't it? And that is exactly the advantage of the system. It makes maths simpler. How about zero? India was clearly familiar with the idea of zero. Let me give you some evidence. For that, we need to travel to the fort at Gwalior. Well, there is a stone tablet at the Gwalior fort that dates back to 876 AD. Now this tablet has a notation for zero. Not once, but twice. It mentions a piece of land that is 270 by 187 units long, and in the number 50, which refers to a daily gift of 50 garlands. This is the first recorded evidence of the zero we use today. Though some believe that Indian mathematicians like Aryabhatta and Pingala knew about it earlier. In fact, the Indian mathematician Brahmagupta also talks about zero. He writes that when you subtract a number from itself, you get zero. He added, the sum of 0 and a negative number is negative. The sum of a positive number and 0 is positive. The sum of 0 and 0 is 0. Now, what made India's contribution revolutionary is the use of 0 as a number rather than just a placeholder. This, combined with the other numerals, hugely simplifies all arithmetic operations. This knowledge traveled to Arabia, which was a huge center of learning at the time. When the famous Persian mathematician Al-Khwarizmi studied the system, he immediately saw this could revolutionize mathematics. Al-Khwarizmi was swift to take all these foreign symbols and ideas into his heart and mind and make them his own. His book, Kitab al-Jam wal Tafriq bil Hisab al-Hind, or Hindu Art of Reckoning, played a big role in spreading these concepts. This system then moved to Africa. A young mathematician called Fibonacci was exposed to this system as he lived in North Africa. He received an education from Moorish teachers. He realized that Arabic merchants were able to calculate much faster than their European counterparts, and realized that this was because they were using the Indo-Arabic system of numerals, which was clearly more efficient. Fibonacci quickly realized the advantages of this new system. When he returned to Pisa, he wrote a book that he finished in 1202 titled Liber Abaci, meaning Book of Calculating. This book dealt with the methods of arithmetic in the decimal system, and it eventually persuaded European mathematicians to drop the old way in favor of the new. These two systems led to a divide in Europe. In fact, there used to be mathematical competitions between the two. On one side, there were the Abacists, who used an abacus, and on the other, Algorists, who used the newer Indo-Arabic systems. There's a 14th century manuscript of Boethius's The Consolations of Philosophy. There appears a well-known drawing of this kind of competition that is being judged by the goddess of numbers. Now, Europe at this time was using the Roman numerals. So if you need to write the number 1999, this is how it would look. Now imagine adding and subtracting from this. Much easier to add from 1999, right? Now we know who finally won. By 1500 CE, the newer Indo-Arabic system had won and has persevered until today. The best way actually of seeing who won is by exploring the systems used today. Anywhere in the world, China, Arabia, Africa, Venezuela, languages, font, metaphors change, but the number systems are surely universal. That's all we have on numbers today. Keep watching the Maths Factor for many other interesting nuggets on the magic of mathematics.